I hope you guys are all doing well and enjoyed your weekend. I know it's been a big gray. Hopefully the sun will come out one of these days. Anyway, today we're focused on light sources and interaction of light with matter. And just to give you an overview of where we're going to be heading, today is light sources. On Wednesday we'll talk about light tissue interactions, including things like lasers to blast tattoos and things of that nature and reshape your cornea. Then we'll go on to tools and talk about ways in which light is detected and interpreted. On the 25th, because we have an intervening holiday here, this is a Wednesday, and then the following Monday, you'll have some basics of biology. For a portion of you, that'll be a review. For some of you, it'll be kind of new material, but it'll give you just a sense of the varieties of scales and the different things that we can study with biophotonics. And once again, this is the practical biophotonics diagram. It's showing you that pretty much all biophotonics applications involve these different components: a light source, a subject, a sensor, and an interpreter. Okay? This is what we're going to be covering over the next couple of weeks. And today and Wednesday we have hands-on components. Today you'll be learning about light sources, and on Wednesday you'll be actually measuring your hair. Okay? And then that'll be the data for your first lab report. So, today's main points: there are various sources of light. Each of them has specific characteristics, and they also have different energies that are emitted. Okay? An important point from today. By the way, the lectures from the prior two sessions are online as PDFs. We don't have the videos linked yet, but we do have the PDFs up there. Hands-on, you're going to be observing the characteristics of various light sources with this tool. The NASA handheld spectrophotometer. This is the $4.99 version of, no, it's actually, they send you these for free, you just have to build them. But these are very, very handy tools, and this will be the low-tech version. We'll be using a higher-tech version shortly. This will be the low-tech version of observing specific information about light sources. Have any of you used things like this before? You point them at the light and you see what components. How many? Can you raise your hands if you've used something like this before? Okay, good. So a portion of you have used these. You can help the others as they're struggling to figure out what they're seeing. Okay. And then we're going to end with light interacting with matter in a combination of different ways simultaneously. And all these lasers tend to give out after a while. Okay. So, what are some sources of light? Let's hear your thoughts. The sun. Okay, good. Hot materials heating up and radiating light. Okay. Any other ideas? Sources of light? Yep. Okay. How do you think light bulbs work?
Probably
Heating up something and radiating energy? Yeah, okay. So far, you guys have all given me the same example. Let's hear some other ones. Let's see. Fireflies. Okay, and what do you think that, how do you think that works? You don't tell me the specifics, but let's hear. Okay, what do you think?
I think in cases like fireflies, it's a symbiotic relationship with bacteria gives off don't have bacteria in there.
No? There can be things like that, but that's not the case in that situation.
they're approaching it with the ATP, and then when it breaks the ATP, the energy comes out and it's a light.
Chemical reaction. Chemical reaction utilizing energy to give off light. Okay?
So then for like an anglerfish, which is bacteria, how do they
You know, I need to know that. I need to read up on the specifics of anglerfish. I know that they do that; they give off light, but I don't know how they signal the bacteria to do their thing. But it would also be a chemical reaction. When an animal gives off light, it's called bioluminescence. Okay, and those animals in complete darkness give off light. So there, in that case, it has to be a chemical reaction. Any other ideas how you can create light? Radiation, you mean, can you tell me a little more about that?
Gamma radiation.
All of those are forms of light, the whole electromagnetic spectrum. But
that happens when
Okay, so you're saying some kind of reaction, but you're talking more at a subatomic level now. Okay. Any other ideas? Did you guys ever have glow-in-the-dark stuff when you were growing up? How does that work?
It absorbs photons, something that the pigment absorbs photons
Uh-huh.
and then gives them off at a lower level over time.
Uh-huh. And we'll be here looking at the specifics. And what's the thing a lot of your, well, I don't know if a lot of your professors use this, but we use them in here. Point at things. Lasers, that's another source of light, right? Okay. That again behaves totally differently. Okay? So let's look at some of these. First, before I go into that though, can you tell me about some basic differences in some of these things that we've talked about? Can you think of anything? Like we've talked about the sun, we've talked about light bulbs heating up, we've talked about chemical reactions in organisms.
Well, a light bulb tends to give out light in all directions of the universe, so they're very
Okay, so there's a directionality to the different light sources.
what wavelengths they give off with the different colors.
Excellent. The different energies that come off, the different wavelengths make them look different to us. Anything else? You guys ever stood next to a light bulb? Heat. Ah, okay. Have you ever stood next to a fluorescent bulb? As much heat? Okay, so differences in the amount of other energies that are given off that we don't see with our eyes, but we can feel. Okay? So these are just some of the differences. Now let's go through and look at these individually. So the ones that we're going to be looking at today are incandescence. So that's where we heat something up, okay? And it gives off a range of energies. Electroluminescence, which is the LED. Nobody mentioned LEDs, but you guys remember LEDs come in different colors. We've got different colors of LEDs. We've even got white, okay, blues, reds. They come in all different colors. Tend to be a lot what we use on displays. You know, when your phone blinks green to tell you that it's connected, that's an LED. Lasers. Fluorescence. Okay, now this is kind of a tricky source of light. It's kind of an odd one. I have to add in higher energy into the system so I can get lower energy visible light back out, or not visible light. Then we have phosphorescence, which is similar to fluorescence, in that you have to put higher energy light in, and then it gives off light, except phosphorescence does it slowly. Fluorescence does it instantly. We'll be seeing examples of that. Then we have Chemi and bioluminescence. Chemiluminescence means you have a chemical reaction, you give off light. Bioluminescence is just when that happens inside a living organism. And then we have something known as blackbody radiation, which is really a form of incandescence. It's just a pure form of incandescence, and it's getting back to that idea that we talked about, where if something's made up of vibrating atoms and molecules, that it gives off a spectrum. Depending on its temperature, it gives off different ranges of energy. We'll be talking about that. Right? So, let's start off with incandescence. How does incandescence work? You basically heat something very, very high, to a very high temperature. That heating, okay, causes a whole bunch of electromagnetic radiation to be generated, and depending on that temperature, different energies are given out. Right? So, if I take a light bulb and basically pass electricity through these little thin wires, for a regular incandescent light bulb, that electricity, that wire has a lot of resistance. So as the electricity is trying to go through it, it actually causes a lot of collisions. That cause heating. Okay? And that heating of that filament makes that filament get really, really hot. Okay? By really, really hot, I mean thousands of degrees Kelvin. Do you guys know what I mean when I say Kelvin? Okay, Kelvin is kind of like centigrade, except there's a 273.15 degree difference in there because of absolute zero, but we'll talk about that in a moment. So a tungsten light bulb glows at 2700 Kelvin. So that's very, very hot, okay? Very, very hot. Now, in general, in these light bulbs, you notice that they have a glass covering around them. We don't tend to have light bulbs that are just out in the open air, right? And that's because they would instantly catch on fire and burn up, and the wire would be gone.
I've done that before, actually. Taking a broken light bulb.
And you plug it in, and you go, poof, basically, okay? Do you guys ever see those old movies where, you know, there's the people with those big fancy cameras, a big wooden box, and they're covering their head with a big black cloth, and they've got this tall thing, or they've got an assistant that's holding this tall thing up there with this little powder in there. Well, that's what they were basically doing. They were basically igniting some powder to get a bright flash of light. That was the original flash. And if you guys remember the old time, back in the 70s, we had these little cubes that you'd stick on little simple cameras, and these little cubes, you'd pass a jolt of electricity through them, and they'd basically burn out, giving out a big flash. That's what would happen to your light bulbs if these were filled with oxygen. But they're filled with argon, usually, or some other kind of inert gas. And that inert gas keeps the wire heated to a really high temperature, but it doesn't have any oxygen in there to mix with it to burn. Okay? So it keeps your light going, and usually they have a certain amount of lifetime to those lights. You know, they go out. And the problem with these lights is that about 90% of the energy that's put into them is given off by them in the form of heat. Okay? So they're great if your apartment's cold and you got all these light bulbs going, because they're another form of heat, right, into your room. But if you don't want that in the middle of summer in Davis, it's not the greatest thing. Okay? So they waste a lot of the energy. Basically, the sun is a big incandescent, big fireball, right? And that fire, that heat, makes the temperatures inside the sun very hot, which causes it to emit all kinds of electromagnetic radiation, including the light that we use for surviving, okay? Giving energy to our plants and ourselves. So that's incandescence. Then we have electroluminescence. Here's an LED, a green LED, a red LED, blue LED. I can make these in all sorts of colors now. Red used to be the only real practical one, but now you can make all kinds really easily. And here it's an optical phenomenon, an electrical phenomenon, where something like a natural blue diamond can emit light when you pass current through it. Now, these LEDs are not blue diamonds. This is how some of these things were discovered. And you basically do it with semiconductors. Okay? You put two different materials real close to each other, you pass electricity through them, and as the electrons jump from one material to the other material, there's something known as a band gap, and that band gap corresponds to the color of light that you get from this material. Okay? So by using different materials, you can, in a sense, tune or change what that band gap is and get different colors of light emitted. Okay? Now, it emits incoherent monochromatic light. Okay, so monochromatic, what does that mean? One color, okay? So the light from an LED, which is very different from an incandescent light, tends to be of a unified color. Like, for example, we see a red LED, a blue LED, a green LED. When we have an incandescent light and we heat something up, we tend to see a range of colors. Okay, in general. Not always. You can heat something up and only see red. But in general, the incandescence gives you a broad range. The LEDs give you a narrower range of energies. Okay? And the energy efficient, it's 2 to 4 times more efficient than incandescent, and now they're becoming even more efficient. Yes?
So if that LED light, you have to change the colors, is that just changing the band gap?
It's different materials which effectively change the band gap, changing what the energy is that's released upon passing electricity through it. Now, these are starting to get to be up to 10 times or more efficient than incandescents. We're actually likely to, I don't know if you guys have already seen this, but already at the hardware store you can buy light bulbs that are made up of a whole bunch of white LEDs. Okay? Because those are 2 to 4 times more efficient than fluorescence. And fluorescents are 2 to 4 times more efficient than incandescent. So the next wave is a whole bunch of LED lights.
They're monochromatic. How do you get white light out of it?
Out of an LED?
Yeah.
You mix 3 different LEDs is one way. So when you see a white LED, it's done in one of 2 ways. It's either a red, green, and blue that give approximately the same amount of light out as perceived by our eye, fooling us into thinking it's white light. That's one way. The other way is they act kind of like a mini fluorescent bulb, which we'll be talking about fluorescence in a second. But fluorescence gives off ultraviolet light, which then interacts with a coating in the inside of the bulb, which then gives off the different colors to us being perceived as white light. Okay? Those are the two primary ways in which you get a white LED. Now, you guys, LEDs come in a ton of different sizes and shapes. And you guys have seen traffic lights made from LEDs? You know, that's now the standard. That wasn't the case before. For a long time, we never had LED traffic lights. And now even the rear tail lights of cars are all LEDs. Part of the reason that LEDs are so interesting and special is that LEDs are very fast to turn on and off. The moment I pass electricity through them, they give off light. Incandescent lights, even though to you they appear, to you and I, they appear like they're instantaneous, they're not. Incandescent light, you have to pass electricity through it. The wire has to heat up to temperature, and then it gives off the appropriate color that you want. But there's actually a ramp-up time in heating up that filament. So believe it or not, when you're going 60, 70 miles an hour, and somebody in front of you slams on their brakes, if they have LED taillights, you get the message, I think it's somewhere in the range of 30 to 50 milliseconds earlier, which allows you to brake faster. You hit your brake a little bit sooner, and it saves you, 10, 15 feet in terms of your braking. So they're actually safer. You're actually safer tailgating somebody with an LED taillight than you are somebody with a regular incandescent. But the basic idea is that that's all being converted now. The reason why I don't think it's been such a big, widespread thing is because they're more expensive, and two, they last a lot longer, so you don't change your taillights as often. Okay? So, believe it or not, manufacturers think about that. They want a certain failure rate so that you have to replace stuff. Okay? So that's why we don't have all of them converted yet, in my opinion. Okay, the next one, the laser. Okay? Light amplification through stimulated emission of radiation. Boy, that's a mouthful. Okay, that's what laser stands for. And the lasers have only been around since the 60s. Okay, that's when people were first starting to do research on these things. And what's interesting about lasers is that they're monochromatic, again, only a single energy, except in this case, really much, much narrower range of wavelengths given off by a laser than by an LED. They're coherent, which means that the waves travel in a way that they know about each other. They're all traveling it's not that they're traveling synchronously, but if you know where one wave is, you can recomposite where all the other waves are, which is different from incoherent light. They're directional. You notice that I can point this thing, and yes, it does get a little bit bigger as I point farther and farther away, but not much. We can make them all go in a certain direction. And they range from ultraviolet to visible to infrared, and you can even make lasers that are tunable. I can literally change a dial, and it changes the energy that's coming out. Okay? And the really amazing thing about lasers, what makes them so special and what makes them usable for going in and taking off layers of your cornea in your eye, okay, which is something pretty delicate, right? You want to be pretty careful when you're doing these types of things, is that you can pulse them down to femtoseconds. So femtoseconds, 1 times 10 to the minus 15th seconds. I can pulse a laser, and why might I care about that? Why do you think you might want to be able to control the amount of time that you have a pulse of light interacting with living tissue?
To control how much energy it puts into that tissue.
Yeah, to control the number of photons that you're delivering, basically. If I have a laser of a certain power, and I keep it on, and it's just on, I'm constantly delivering a stream of photons there. I may deliver too many. I may destroy the tissue, but if I can control the length of the pulse, the amount of time at which the tissue is exposed to that laser light, I can control how much energy I'm depositing, and therefore have a really fine-grained control. All right? Now, let me see if I can get you. So this is a site that talks about atom-light interactions, and it has some interactive components. Let's see if they still load. That will show us how a laser works. they don't work, I'll show you the static, but if they do work, I'll show you the animated here. I don't know why it's taking so long to load. This is what happens when you upgrade. Okay, come on, come on. Okay. Let's switch over here for a second. I'll tell you about this one. We'll see if in the meantime that one loads. Okay, so this is one of the more basic forms of lasers, okay, the ruby laser. And by ruby laser, I mean I have a chunk of ruby, okay, that I'm using at the base of this laser. Guess what? These are not ruby lasers, okay? The $30 lasers are not going to be ruby lasers, okay? But when they first figured it out, what they did is they had this material, this ruby material, and it's represented here in red. And they had, of course, it has atoms that make up the material. And it had a mirrored surface at one end and a partially mirrored surface at the other end, and a flash tube, something that keeps on flashing light, okay, at a certain rate. And what happened is the light would flash and it would excite the atoms in the ruby rod, okay? By exciting them, it means it would impart energy upon them. It was tuned to be the right amount of energy that it would make those atoms excited. Those atoms would be excited, and then they would go back to their non-excited state, and they would release a photon. So the excited atoms emit photons in random directions, okay? Those would emit in all kinds of different directions. Well, the ones that were traveling parallel to the axis would hit the mirror, and then they would start traveling back through. They'd go to the mirror, start coming back, and they'd hit another atom, okay? And that energy would be tuned such that they would be absorbed and then be re-released. But what was happening is, if it hit an atom that was already excited, then 2 photons would be released. So you quickly had a reaction that got greater and greater and greater in intensity, and hopefully that little Java applet works, and then I can shows you that in animation. But you'd effectively were getting an emission of a photon, it was bouncing back, it was hitting another atom that was already excited and was about to release a photon, but it would hit it, and it caused 2 photons to leave. Those would bounce in the mirror, come back. Maybe they would hit another 2 atoms, and now you'd have 4 coming through. And then you'd have 8 and 16, and they would keep on multiplying, okay? Until you had enough of these that even the partially mirrored surface would have enough photons going through that you've effectively caused a laser. You've caused lasing, which means that all these photons now can go out in a coherent directional way, and you've got your red laser. Okay? Now let's see if that thing works. Okay. So this shows you photon coming in from the flash bulb. See, it comes in and then gets re-emitted. Photon comes in, gets re-emitted. Let's do this faster and faster. Notice every once in a while now, 2 of them come out, because it's already excited, but the other one comes so fast that the 2 of them come out together. Okay? So a photon strikes an excited atom, and the atom emits a new photon just like the first one. Okay, now let's see if we can go on to the next step. There's another Java applet that has to load now. I don't know why it became so slow. But anyway, so what's happening is then you get enough photons of the same energy, the same color, because remember, how did we get those to begin with? We flashed. It was a specific quantum energy that was absorbed by those ruby atoms, which meant they released a very specific wavelength, which meant that all of those were the same. Okay, let's see. So now we put in this flash bulb here, what they call an energy pump, and we start to see what happens. If we didn't have the mirrors, you see that basically the more energy you put in from flashing, this energy pump that we were talking about before that flashes, the more you excite the atoms, the more they bounce into each other, excite each other, and photons travel off together. Now, let's put it all together. Okay. Now we've got our atoms inside. Okay, we've got our mirrors. And we start adding energy. See, every once in a while, a few get out the other way, the partially mirrored surface. Now we add in a lot of energy. And now you've got your lasing going on. All these photons are together and they're lasing. They're putting out the same energy. If I convert it into a wave view, what you see is I have a whole bunch of waves adding up, and then some get through the partially mirrored surface, and I get a wave of monochromatic light coming out the other end. Does that make any sense? Okay, there's an amplification going on here, and the amplification is going on because as they get excited and release photons and then interact with other excited atoms, they release more photons and more photons and more photons, and the more you have, the more they excite. It's like a chain reaction. Okay? Yes?
So are the dark molecules the ruby molecules?
Yeah, in this case, you could call them the ruby molecules. And they're moving, right? Because everything is moving all the time.
What is special about ruby that makes it not like diamond or sapphire or any other? What is it about ruby?
You know, I don't know the exact answer of why they picked ruby first. My guess would be that they were relatively uniform, and so they could get a relatively good-sized crystal that was large enough and that had the right energy range, because a diamond might not absorb the right energy range to give you a laser in the red.
I don't know about the time they start to make synthetic.
You know, we can look up exactly why they picked ruby. In the story, the original story, do you know, Jim, by any chance, why they would have picked ruby as the first material? I'm just guessing that it had the right wavelength, right absorption. They could excite it, and it would, you know, it had the right balance of.
Yeah, well, because, you know, the ruby, it depends on the transmission level of ions that are in solution to get the right frequency. So it's a readily available material that had that characteristic.
I'm guessing that it was because of the specific wavelengths that they got. So they could also do something that they could see. A diamond might have given you something in a range that was not visible. Then they would be much harder to test, right?
So it doesn't light up instantly because enough of the photons have to get excited. So wouldn't LED be faster?
You know, this process is so fast that it's actually faster than the LED process. And now we have all kinds of solid-state lasers. We have different ways in which we get lasing. This was just the way it was discovered. The way that this green laser works, it does something called frequency doubling. It's actually an infrared laser that then gets frequency doubled to give you green. There's many, many other techniques now, but they're much more complex to understand.
So it's like a chemical laser.
Yeah, again, what you're basically having to do is you're having to find transition that you need, the energy transition that you need, and have molecules that are stable enough to do that repeatedly and not decompose and not have some other reaction happen. So it's just a question of something called dye lasers. They actually make liquids with special dyes in them, and that's how you get tunable lasers. You change that dye. That's one way you get tunable lasers.
Are the photons that are being emitted with light like flash? If not, then don't they have like effect of that?
Remember, the photons come from the ruby atoms being excited and then coming back down to their ground state. So the ruby atoms aren't changing. They're just this intermediary that's taking up the energy, releasing it, taking up the energy, releasing it. If I turn off the energy source, then of course it won't work. So if I turn off the flash source, you're stuck. But if I don't, if I keep that going, the ruby doesn't go bad. Okay? Yes?
How far did these travel in a straight line? How far did you see the laser? The early laser, how far did the red light go?
You know, I don't know the specifics of the first laser. I mean, I know that now we point lasers at the moon to figure out how far the moon is, and we look at it bouncing back. I mean, remember, photons, once I let them go, if there's nothing in their way, they just keep going. So there's somebody out there, 30 light years away that just got poked in the eye by a laser. No, I don't know. Because 30 years ago or 40 years ago we made these lasers. No, actually, I guess it's now almost 50 years ago. But if there's nothing in the way, it just keeps going. Photons don't care. Okay. So, next source of light, fluorescence. Okay? So fluorescence. Some atoms can absorb light of high energy and release light of lower energy. Now, we just talked about the ruby atoms. Well, the ruby atoms absorb light from this flash, and then they give off this red light, and you might ask, well, why isn't that fluorescence? Well, the light they absorbed was the same energy as the light they re-emitted. Okay? There was nothing happening. It was absorbed, re-emitted. Okay? In the case of fluorescence, greater energy is absorbed. Okay, so an electron is brought up to a higher energy state, and then before it comes back down to the ground state, it relaxes in some kind of vibrational and rotational way, and then re-emits the ground state. So the energy that was put in is different than the energy that was gotten out. In fluorescence, you put higher energy in, some other kind of relaxation process happens, and then you release a photon. Which means, if I excite my fluorescent material with red light, what colors can I get out? Well, what kind of colors? What's lower? Infrared. If I put in red light in and something fluorescent, I'm going to get infrared back out. If I put in green light in, what kind of colors could I get back out? If I put in blue light, what kind of colors could I get out? Okay. If I put ultraviolet light, what colors could I get out? All the colors of the rainbow I could get out, depending on what the transitions are and how the relaxation happens. Okay. Now, it's much more efficient than incandescent. So how do these are fluorescent bulbs right up here. Okay. These lights are fluorescent lights. Okay. So these lights, they kind of look like they're giving off white light to me. How is that possible? How would I get white light? Huh? The coating that's inside, exactly. And actually the coating, some of these, the thing that's confusing is that these light bulbs have you guys ever broken one of these? Okay. Some of the guys go, yeah. They pop, right? And then what do you see inside? See anything inside? Come on, all you bulb breakers out there.
Basically disintegrates when I did it.
It disintegrates,
Yeah.
but there's a little bit of powder. There's a powder in there. Okay, the powder is lining the inside of the bulb. Okay? That powder is made up of different materials that both fluoresce and phosphoresce, to be honest with you. Because if you turn off these lights for a little moment, you still see a little bit of light coming off them. So there's a combination of fluorescent powders and phosphorescent powders. So what? I'm going to contend that inside that light, there's ultraviolet light being made. Okay, ultraviolet is being made by passing electricity through a gas, actually, inside there. So that gas gets electricity passed through it, gives off ultraviolet light, and then that ultraviolet light interacts with those powders to create what we perceive as white light. But how can it do that? What is white light?
White light would be all the colors, but you don't necessarily need all the colors.
Excellent. Yep.
So I'm guessing the powders would be a mixture of atoms, but different elements, which would give off different wavelengths of light.
And when you guys look at the fluorescent lights with this, you'll see exactly how you get the white light, the perception of white light, okay? You will get to do that. Now, you guys have noticed there's a variety of things that are fluorescent, including, we looked at the license plates, right? That was one thing that we looked at. So this is what they call a black light, and if I put it on my shirt, probably you guys can't see it, but I see lint. Okay. There's also, I told you guys before, the detergent that's used that makes the whiter whites. That detergent actually has little flakes. It's kind of like what's inside your light bulbs, your fluorescent light bulbs that make the material glow when you're out in the sun, make it appear white or white. These are some rocks, okay, pretty dull looking. The moment I shine the light on it, okay, these rocks have fluorescent materials in them, compounds in them, that when I put in the high energy bluish ultraviolet light, I get, in this case, yellow, in this case, orange, in this case, yellowish orange. You guys see that? Okay? So a lot of naturally occurring materials fluoresce. And actually, pretty much everything alive, living things fluoresce to some extent. Yes?
What exactly is a black light?
A black light is just a light that gives off high energy blue and low energy ultraviolet. That's all the black light is. Somewhere between, usually between 380 and 400 nanometers, or 380 and 420 nanometers.
Just like a real high end.
High end of the blue. Yep, high end of the energy of the blue. Now, your skin fluoresces, my skin fluoresces, cancerous lesions can fluoresce. All these things can give off some light, just not as much as those rocks.
It's like you get your sunburn.
Yeah. Though sunburn tends to be, the worrisome sunburn tends to be more like 360, 370. So this isn't, it's energetic, but it's, I mean, I wouldn't want to put it in my eye, and I wouldn't want to just sit there for a long time, but, you know, momentary, a few minutes, not even, wouldn't be that big of a deal. Okay? Now, what you might not expect, did I get this green laser to work? This is olive oil. Extra virgin olive oil. Okay? First press. Okay? It's a little old now, but it's still olive oil. If I take this green laser and I point it at my arm, looks green. If I put it in my hand, looks green. Boy, it's bright. Okay? But what do you think will happen if I point it through this olive oil?
Green.
Okay? Let's try the thought experiment with the red laser. I'm going to put the red laser through. Comes out red, right? A little bit scattered. What does it look like through the oil? Red, right? Makes sense. Okay, so what did we say the green was going to do? If I can get this green laser to work. This is a high-power green laser from China. They don't really follow the rules. So Dennis Matthews brought these back. I don't know if you guys remember, but I'm going to shine it through. Here we go. What does it look like? What does it go through as? What does it bounce off? Some of you can see behind me or on the side. Okay? So what the heck is that about? Yeah.
Would that be the laser bouncing off the oil particles? Making that orange and then everything else is passing through and
The laser's bouncing off the oil particles. How am I getting orange?
the photons are hitting the electrons, and the electrons are creating the orange color. Green right there.
So you think somehow the green is being absorbed and then I'm getting a re-emission by something? By the oil itself? Okay. What could do that in the oil? What might care about green light?
Probably the remains of chlorophyll and other pigments and stuff still floating on the
Chlorophyll. In this case, it's primarily chlorophyll. Chlorophyll fluoresces. Chlorophyll takes in the higher energy green light and gives off the lower energy red light. Okay? Now here's a little hint that will come back to haunt you in about a month or so. Okay? Chlorophyll. Okay? Chlorophyll. Plants are green and chlorophyll is what color? Green. Where do plants take their energy from? You guys, any of you guys study photosystems? Ah, they like red, huh? The red is what they use for creating their energy. So what do you want to do with all the green light that's coming at you from the sun if you're a plant? You can reflect it off, but some of it you could turn into red, which is what you want, right? You want red. So you can do a few little tricks, okay? But chlorophyll is an interesting pigment. And if I take a bunch of spinach and you mush it up real good, and then you shine either a black light, you know, I don't know if you guys can see this, I'll turn this off again. This is the black light. Put on the oil, see what happens? Not quite as pronounced, but you see a little bit of orangish. Okay, not quite as good because it likes the green better. Because you do still have to match things to the energy levels inside the chlorophyll. But if I take a whole bunch of fresh green leaves and mush them all together with a little bit of solvent to extract out some of the chlorophyll and the other pigments, and I shine that laser onto there, it just glows bright red. Okay, it's pretty amazing. It's pretty impressive. Okay, so that's fluorescence. This is a diagrammatic way to show you. Fluorescence, I absorb blue light, high energy. I go to an excited state, energy state within my compound. I relax vibrationally and rotationally, and then the electron goes back down to the ground state, emitting a lower energy light that was brought into it. So it emitted green light in this case. All right? And we can excite something with, this is showing you want to get the kind of purplish violet, ultraviolet light to go onto, for in this case, a rock, and then you can see the blue light that's emitted from the rock. It's just always saying you that you have to put higher energy in than you get out. So what do you guys think happens when you turn off the high energy light? Do you still see the fluorescence? Is this thing still glowing red? So what's an observation you can make about fluorescence? It requires an external energy source. It requires something to come in and give it the energy that caused the fluorescence to happen. The moment it's gone, it's gone. Okay, so now let's look at phosphorescence. Phosphorescence. So I have a little patch here of glow-in-the-dark material. Okay? It's still a little bit bright because it wasn't in total darkness, so it's still giving off a little bit of light. Do you guys see that? I'm going to put my black light on it. Okay? That was just a way of supercharging it. Okay? And what is it doing? You guys still see it? Okay? Still giving off some light. Is the light blue that it's giving off? What color is it? Okay, it's like a greenish yellow. Okay? So in phosphorescence, this is fluorescence over here. I go to a higher excited state, I relax vibrationally, and then I emit something in lower energy. Well, to actually get phosphorescence, I have to go through something called an excited triplet state. Certain compounds, the way that they deal with this extra energy, okay, certain molecules, the way they deal with this extra energy, is they go through an excited triplet state. And then from that state, they go back down to the steady state, the ground state. And that is a process called phosphorescence. Okay? Now, this is purely the way that those molecules are constructed decides if fluorescence will be dominant or if phosphorescence will be dominant. You can actually have both things happening. That's the interesting things about molecules. There are so many of these different energy states and configurations that you can have all these things happening simultaneously. It's just a question of which is dominant. Okay? In this material, the dominant characteristic is phosphorescence. The thing that's interesting about phosphorescence is that it's slow. Okay? Fluorescence, the moment I turn off my energy source, this is a patch of some different phosphorescent materials. I shine my light on it. The moment the light's gone, the color's gone. Right? You guys see that? Incredibly fast. Actually, nanosecond type fast. Okay? Very, very quick. Phosphorescence, on the other hand, lingers. Phosphorescence can linger minutes. Okay? It gets weaker, but it can linger for minutes. And that's one of the really big differences between phosphorescence and fluorescence. Okay? Question about that? Fluorescence, phosphorescence? That will come back to haunt you. That difference, okay? You will be asked about that difference at different times in this course. Now we move on to Chemi and bioluminescence. And you guys are very familiar with chemiluminescence in the form of light sticks. Right? You guys all used light sticks before? Okay. So, light stick. Nothing, boring, right? Nothing's happening. I crack it. Chemical reaction. Okay? I've mixed different chemicals. This is a particularly bright one, which is good. You guys will need this for your next stage, your hands-on piece. But anyway, what I've done is I've combined a combination of different chemicals, and when they're put together, they give off light. Because they create an intermediate excited state, which then when it goes through the ground state, emits light. Okay? If I have that happening in something living, then all of a sudden, we call it bioluminescence. And we hope we're going to get your graduate student to talk to you about bioluminescence for a whole lecture about how it happens in the well and how it's used in research. But effectively, it's you mix two things together, you get an intermediate product, excited state, which then leads to products and light. So over time, this goes away. It doesn't continue forever. That chemical reaction has a certain rate at which it happens. You can slow it down by cooling it. You guys know certain chemical reactions you can slow down by cooling and speed up by heating. But it is a chemical reaction. And any of you guys watch CSI or have seen things like that? You know, and they say, oh, there's traces of blood. Okay, so one thing they're doing is they're going through with their black light and looking for bodily fluids. Because bodily fluids, I said, a lot of things that come from living organisms fluoresce. That's one thing they can do. You can look for blood and other bodily fluids. But you can also have a chemiluminescent reaction. And the chemiluminescent reaction, there's a property of blood that if you mix something called luminol, okay, luminol reacts with iron. And when it reacts with iron, it forms a reaction that gives off light. So if you were going somewhere in a crime scene and it looked like just regular carpet, and you spray your little luminol on there, you turn off all the lights, and you see glowing, this, in the CSI world, means there's blood there. Okay? Something happened. Now, really all it tells you is that there's iron there. And iron is a part of hemoglobin. That's why they assume it's blood. But if you were doing this in a factory that works with iron oxides or different forms of iron, it'd be worthless. Okay? Because you can't tell the difference. All you know is there was iron there. But this is a form of chemiluminescence. They spray it, lasts about 30 seconds, and you see this glow. And then the reaction's exhausted, and you don't see anything anymore. Okay? But that's what they're doing when they're doing that little spray bottle thing. Okay, they're spraying luminol. Okay, last one. Last source of light. Blackbody. So, anything that is vibrating emits a well-defined spectrum of energies depending on its temperature. Okay, that's what we talked about. So, what that means is that you get a range of wavelengths emitted. For example, if you have an object that's at 1,000 degrees Kelvin, okay, so 700 and some degrees centigrade, it has a spectrum like this. It gives off mostly in the infrared, has a peak in the infrared, and then it gives off a little bit of red. So if you were looking at that, it would look slightly red. Okay? If something was at 5,500, it would have a spectrum that looks like this, in terms of a blackbody spectrum. And that would give off radio waves, infrared, visible. It would have a peak here in the visible light, so it would look to us as kind of a mixture of all the colors, which we would perceive as white. And then if we go even higher, 30,000 Kelvin, we start getting UV and X-rays also emitted, okay, by that source. So something like the sun can emit a whole range of wavelengths. Now, what that means is if I have an object and I heat it up, is it hotter when it's red or is it hotter when it's white? And why?
More energy has to be put into it to reach that color spectrum, that color.
It has to do with the temperature of the object to get to that spectrum, that range of colors, yes. But why would white be hotter than red? Because you need the whole spectrum, okay? And here, let me show you an applet called Spectrum Explorer. And what this applet does is it shows you the wavelength, the temperature of the black body, right now 5,700 degrees Kelvin, okay? This is showing you where the colors of the rainbow are on here. And notice they range from about 4 times 10 squared, so 400 nanometers, to about 700 nanometers. Okay, that's the rainbow. And this shows you an object that's 5,700 degrees Kelvin has this profile of energies that it gives off. Okay? That profile of energies to us looks like this color. So it looks like whitish. Now, I can come in here and I can raise the temperature and it looks like even more bluish. So actually even hotter than white hot is blue hot. Okay? Even hotter. And it keeps going up. Okay? If I go in the other direction, you see that white, something looks white, then it starts looking orangish. As I lower the temperature, it looks more orange. And then as I lower the temperature even further, it starts to look red. I'm still pretty hot. I'm still over 1,000 degrees centigrade. What is our body temperature? What color are we going to emit?
Infrared.
We're going to emit in the infrared, but where in the infrared? What's our temperature in degrees Kelvin? Body temperature. Well, let's do the calculation. 273 is equal to 0 centigrade.
Oh, wait, sorry, I mean, I got confused. So we got 300.
So we're about 310, okay, because we're about 37 degrees centigrade. Roughly, that's roughly body temperature in centigrade. I know you're not used to thinking of it that way. You're used to thinking of 98.6 Fahrenheit, but it's about 37. 37 plus 273 is equal to 310. So let's type in 310. And let's see where we emit. 310. Okay. So let me change the scale. X-axis range. Let's go from 200. Now we're going from, this is 200 nanometers right here. See, it's times 10 to the fourth. 200 nanometers to 13,000 nanometers. And notice that our peak is somewhere right in here. So we peak somewhere around 9,500 nanometers, which is well into the infrared, okay? Because visible light would be in here. This is 1,000 nanometers right here. Right? 1 times 10 to the fourth is equal to 1,000. So visible light is right here. So we don't emit visible light. That's why when you're in the dark, you can't see where other people are. Okay? That's the basic reason. But the camera that is sensitive to this region of the spectrum that I brought in, that infrared camera, can see us. Okay? That's where our maxima are. And this is an interesting program because it allows you to overlay all kinds of spectra from the sun and from different chemicals. If you guys want a copy of it, let me know. I'm happy to show you where to get it. Very, very interesting program if you're into that kind of stuff. So, by the way, you can overlay the solar spectrum. That's what the solar spectrum looks like. And that allows you to figure out that the sun is roughly 5,800 degrees Kelvin in temperature. Okay, as perceived by us on Earth. And that's when you hear, have you guys ever heard of star temperatures? People talk about blue stars, or red suns, blue suns, things like that. Stars are suns. So if you've heard of that, all they're saying is because of that color, they know the temperature of that star. And the temperature of that star tells them something about what part of the cycle of that star's life that star is in. And you can tell it by the color. So you get the spectrum of that star, and you can match it to a black body curve, and you can figure out roughly what temperature that star is.
So the older it gets, the more it tends to change, right?
From what I know, they peak up into the blue, and then they go towards the red, but then they can also explode, and then they can come back. So it's more complicated than just one progression. On average, it's something, but... Okay? So you guys remember, the infrared camera, the thermometer, all use that fact of where we emit in the infrared. And as usual, you saw the glasses block the infrared, eyes give off a lot of heat, people have cold noses. These are just some parrots. You see, parrots have the greatest heat given off under their wings. This is an otter, very good insulative skin. These are chickens, and the heat's given off by their feet and their beaks. And this is a boa constrictor, which is a reptile, cold-blooded, not much heat coming from that animal. Okay, so as a recap, sources of light, we went through incandescent with Blackbody being a pure form of incandescence. We went through the LED, the laser, fluorescence, which required inputting energy to get energy out, and phosphorescence, we also did that, but it was on a different time scale. And then we did the chemical reaction with Chemi and bioluminescence. Okay, questions about these sources of light? Yes?
The leader between fluorescence and phosphorescence, is that one is longer, or is it a different process?
It's a different process. It's a different relaxation process. It goes through that excited triplet state. But from the point of view of the way you need to think about it is primarily that difference in time. They always lead to lower energy coming out. Okay, and that difference in time. Okay, so now you guys, we're going to do an activity. And you're going to look at all these different forms of light and figure out something about their spectrum. Okay? Now, I have a worksheet here that will help you gather your thoughts. And as soon as you get it, you might as well start. Work in groups of 2. And you're welcome to talk with others, but in 2 is a good place to start. And go through the first part, the think part. Go ahead, Tom, and look. And if we might have 23. So go ahead and talk with each other. But you might want to start by yourself, just thinking what you know about these different sources of light, based on what we just talked about. You're basically going to do a think share for this first part. You're going to think about what you know about these sources of light, and share them with each other and potentially other people around you. In the meantime, I'm going to walk around and give you guys some of this equipment for the next stage. Please never point a laser at somebody else. And whenever you're looking at a laser, just point it at a piece of white paper. Okay? You never point it towards your eye or point it at someone else. Go ahead and do the first part, think and share. You're not pointing at yourself. Okay, guys, fire alarm. Everybody out. Take a sheet with you. You can talk about outside, the sheet. Oh, did it stop? Seriously? That was just a test, guys. That had been a real fire drill. You guys keep working on your sheet. Don't keep looking at everything else yet. Keep working on it. We're going to start talking about it in a few minutes. I'll give you guys 5 more minutes to do the first thing and the share post, okay?
UV and yeah, it doesn't, it might not be a lot of work here.
Okay, 2 more minutes. Here's what you can share. And then we'll talk about it for the second, and then we'll go on and check things out. Okay, guys, let's talk about this for a second. Okay, can I have your attention, please? Are you trying to look at the black light with that? It's tough to see. Okay, so I wanted to hear just some general concepts, thoughts you guys had, any questions you might have. What do you guys think about the sunlight? What do you know about that? What? Which are?
UV,
Okay, so it gives a range. Okay. How about incandescent? which, by the way, for today's work, this is one of the incandescent lights that you're going to be looking at, okay? This is our sun for today. So there's another one on a red light. Can you just put it up so people can see it? That one also has a flashlight at the end, and it has a black light. That has a combination. Halogen versus incandescent. You guys think of anything? Uses a different gas inside, but what do you think it does? Any difference? What they call a halogen light is really a light that just burns at a slightly different temperature. Okay? So it gives a slightly different spectrum than a regular incandescent. LED's white, what do you think that'll be like? What can you tell me about their color? Mixture of different colors. Okay, and we'll see more about that. Lasers, what do you guys think about the lasers? What's going to be special about the lasers? Monochromatic. Okay? And LEDs are going to be monochromatic too, but you'll have to look if there's a difference. Okay? The light sticks, the chemiluminescence. Chemical reaction, okay. Anything else?
Another question.
Yeah.
Is it just different chemical reactions that make like different colors?
Yeah. Yeah. Just different chemical reactions make the different colors. Fluorescent, I saw you guys, some of you were sneaking up and looking up at the sky. I mean, at the light bulbs up there. So what we're going to do next, you guys see on your third page, there's these little graphs here, the beginnings of graphs, okay? And you see how it has 300, 400, those are all nanometer readings. And when you look inside your spectroscope, they correspond to a scale that's in there. When you look up at something, you may have a hard time seeing the scale. You may have to lift up this flap to see the scale better. And at times it'll just be difficult to see the scale. So you just kind of have to get used to where the numbers are. But that scale that's in there is actually in angstroms. Anyone know the difference between angstroms and nanometers? 10 to the 10th versus 10 to the 9th. So when you see 4,000 angstroms, it's equal to 400 nanometers. When you see 6,000 angstroms, it's equal to 600 nanometers. So that's why these two scales work, okay? The one I have drawn on here. Now, what you guys are going to do is you're going to basically draw what you see in here on here, okay? And that'll give you a chance to explore in more depth some of the qualities of these different types of light. So the way this instrument works is you have a slit at the end. I don't know if you guys can all see it. It's kind of a serrated slit. Ideally, it wouldn't be serrated, but it's a serrated slit. You point that slit at the light source. And then you look inside. There's a little diffraction prism here, diffraction grating actually. It's like a slide that what it does is it separates everything into its component colors. And it shows it to you on a scale. And then you can mark off where those energies are. It tells you the energies of the light. Okay? The best one to start off with is to look up at the fluorescent. That's the one that gives you a nice, clear signal. You can also lift this up to tell you can figure out the wavelengths. And you can move it up and down. But you always have to have that slit, at least part of it, pointed at the light. Otherwise, you won't see any colors. The colors are seen over here on this edge. Okay? Why don't you guys all look up at the fluorescent lights? And make sure you see what I'm talking about. Do you guys see it? And by the way, on this graph where it says sunlight, you're more than welcome to go outside the door and look up at the sky. Okay? Now, on this, I say incandescent and halogen. We don't have a halogen bulb today. Okay? These are incandescents, but they're colored incandescents, and the two that I showed you before are white incandescents. Okay? So if you're going to do incandescent white, that's what I would like you to do, not incandescent colored. But you can try incandescent colored just to see what it looks like. Don't worry about halogen because I don't have it. LED white, LED, pick a color. Okay, I sent you guys around. There's these little packets of LEDs, and also there's my light here with the 4 different LEDs. Can somebody lift up? Can you lift that up? Sure. So you guys just have to share these. There's about 4 of these around the room, and there's different colors on there, including white. And then on the back, you see laser, red and green. Again, there's a certain number of lasers going around the room. The important thing with the laser is you take the laser and you shine it on your paper, and then you point your thing at that, at the reflection off the paper, okay? Don't stick this in the little hole and turn it on. Not good. Really bad. At the paper, okay? I recommend you do that. You've been warned. The black light, shine it on paper. Okay? Don't shine the black light directly in. Shine it on paper. Now, paper does something, but you'll have to see. You'll have to look at it and see what you experience. Fluorescent lamp, white, and then fluorescent paint. You can either do fluorescent paint or you can do this fluorescent flamingo. The fluorescent flamingo works. Okay? Phosphorescent paint. You don't have phosphorescent paint, but you have the phosphorescent strips. Can somebody lift up one of those strips? There's like 5 or 6 of those around. And you need to charge those before you look at them. The way you charge them is you shine some black light on them or some white light on them from your white LED. Okay? That'll charge them so you can see them. And these are some Christmas lights. You know, if you want to try some of these different Christmas lights, these are, you'll have to tell me if the Christmas lights are incandescent or LEDs. Okay, and how you can tell. Okay? So you're going to take the next 20 minutes and try to get as many of these done as you can. Okay? Let's start, and everybody do fluorescent light first, because then I got to turn off the lights. Okay? For you guys to be able to do the other lights. So look up at the fluorescent light. If you don't see the colors that I was telling you about, let me know. You should be seeing, it should be very, very clear. And you guys don't worry, you can, as a team, you can just fill out one sheet. It's fine, and then the other person can copy it. Because you usually have to have somebody tell you what they see and the other person draws it.
Yeah, 440, 490, 540.
Yes.
Make sure you get it.
You guys, you want to indicate the intensity of some of these actual wavelengths. You can do it either by the height. The higher they are, the more intense they are, or you can do it by coloring it in thick versus light with your pencil. However you like to do it. But you want to have a sense of intensity.
Okay, so the orange is very good.
Oh, I forget. This one is like the higher number of here. Yeah. I got really confused. So between 5.
Okay, you guys ready to turn off the lights? Oh, we got a few more people.
And it's not.
Looking out the window? Okay.
Our lasers died.
Any more? Looking at the fluorescent? Anyone else? You guys done with the fluorescent? Okay. Okay, your laser is done.
We just borrowed those.
I said about like you mean like 300? Oh wait, now it's oh, no, you're right.
These are actually computers like
Some LEDs. Who wants a list of LEDs? Pass it around. Trying to get stimulated.
and it's like a really bright.
LEDs, you can point directly into the machine.
Okay.
So I guess I'll get just one band, right at 540. It's not Here, we can use phosphorus.
The shape of the thing you see inside your spectrophotometer is based on the shape of the light that you're seeing. So if your light is a dot, you're going to see only a dot. If your light is broader, then you'll see a line. That doesn't matter. That just tells you where the wavelength is.
Are we, when we look at it, are we supposed to look
It's okay.
on the light or something?
Alright.
Alright, that's is about 4, between 4:20, 4:30 all the way. It's like it's
Just the LED.
That's so weird.
there's the purple and 400 and then
I made a whole wall of that stuff for science museum.
I was thinking
Okay, you guys, keep at it. You got 10 more minutes.
It's like a tiny, tiny bit of screen.
looks like kind of a range between this 700 and 650. So this is LED. It's kind of a range, like between 700 and like 650. Maybe 560. Concentrated more, but at 700. Maybe a little higher. Does this one have white?
That's plenty bright.
Yeah. Just like that one.
Anyone need an incandescent light? Anyone need an incandescent white light?
Bad idea.
Okay. That's a very distinctive drawing.
So, you know what everybody goes
It's just got right.
They're like 40.
It's like 540 or something.
That is easier. It's like 4.
Line. I think that it's interpreted.
The laser, the way you're really going to get to see it, you're going to go way down in there.
Okay.
So go like this, and then try to, you might have to move it around a bit.
Yeah.
Sorry.
See it?
Number.
You may have to go out in the light and see what the numbers are. I don't
Yeah.
have a sense of it.
Which one's more advanced? Let's see. LED 650 would be full spectrum. LED red had these couple of
Right, is it near together?
sunlight.
It's certainly the black.
Yeah.
It is.
It's super. That message is
It's like 5 horizontal.
all that's here is yeah. We could
There's a little really faintly between like I just don't see the numbers. You want to look
Trying to figure out if you have any precancerous lesions.
between 500 and 600.
Anyone needs a phosphorescence?
600.
Phosphorescence strip by anyone?
Where's the fluorescent paint?
Fluorescent paint, you can use,
It's the opposite.
fluorescent paint. I might not have given that to you guys. Here's one. Here's fluorescent paint. There's black and white inside. If you can't all get to the fluorescent paint, that's okay. We don't have a lot of examples of it. But you need a black light. You could also look at your driver's license if you wanted to for the fluorescence.
Right.
You could shine up on your driver's
We
license.
use this.
Where did you see the final
We do. We ever get incandescent lights?
Are those incandescent lights?
If you want for the fluorescent paint, you can also substitute the fluorescent rock if you want.
Too bad it feels like the filter.
Mark it as it's rock. You will not all get through fluorescent paint. That's okay. You gotta ask for the black light. There's 3 black lights. There's one there, and there's 2 others.
What's the flamingo?
When you tell me. That one's one of those wild cards. You have to figure out what it is.
What is it?
You figure it out. You can stick the flamingo in the halogen spot if you want, and just mark it as the flamingo. Do whatever you like.
Neon glass gets electrons and neon
What else do we need?
We would like it.
Fluorescent.
Oh, I guess.
Yeah, I did.
Black light.
No, we don't want to do
Oh, wait,
We use the black light.
You want to look at the Christmas lights? Go close. See what they are.
They can make infrared. I think that's what last time.
Oh, right, yeah. Preferably not.
Yeah, because
I get close.
Okay, 2 more minutes.
it's all.
Green, yellow, red. Mighty Mark. You can write it in how you
Anyone want a black light?
Anyone need a black light? Right there.
Are you done with glow sticks?
We were just getting that.
Okay,
We have really fast.
Look at several of these.
You don't have to.
They wouldn't have nothing but
for you.
Right. There's a light stick, guys. You guys need a light stick? You're also welcome to shine a white LED through your finger, or an incandescent light through your finger if you want to.
And they're not.
Oh, good. You're using your powers of reason. Excellent. There are clues everywhere.
Are the wires like Houston?
A lot of times.
Just because we take that much heat.
Yep. Exactly. Okay, guys. Let's stop where you are now. If you can please go back to your seats. Yeah, that's it. Okay, now I want to hear from you guys. I want to hear what you guys saw. I want to hear some thoughts about it. Okay? So, I know we didn't see any sunlight per se, but you saw the effects of sunlight on an upper atmosphere of thin clouds. So, what did that look like? Looking outside, what did you see? It's the rainbow band. Hey, good deal, because where does that light come from? The sun, and the sun is doing what to make light? Fusion, which leads to heat, which gives us that blackbody radiation type curve, which, as you saw, gives you a range, right? So you guys saw that. Even through the clouds, you saw that that's what was happening. Good deal. Okay, incandescent light. Some of you looked at the light here or the one off the red one. What did you guys see? Same basic thing, a rainbow. Because that light is made by heat. Okay? Any other examples of incandescent lights around the room? That you guys observed? Anything similar? Christmas lights? Okay. People agree or disagree? How many of you looked at the Christmas lights? Okay. And what did you see? So even with a green one, you saw a rainbow band? Okay. So it was giving you the whole band, but there were some concentrations depending on what color it was. Some parts were a little brighter. Okay? Anyone try that red light bulb? Who tried it? And what did you guys see there?
Rainbow band, but brighter.
Brighter in the red. Okay, incandescent. All wires heating up. Okay, how about the flamingo? What did people see with the flamingo? What kind of light is it?
We got really discrete lines at 410, 440, 500, and 600.
Discrete lines. Okay. Did other people get that?
Yeah.
So what does that tend to tell you? Huh? It's not incandescent. Good. It's probably not a laser, right?
Probably fluorescent. There's a few different fluorescent materials that each fluoresce at those particular intervals.
Okay, so this is one theory. It's fluorescence with a couple of different materials in there that fluoresce at different energy levels. Any other thoughts?
When the gases inside it ionize, and when that electrons release back down, they emit certain frequencies and wavelengths of light.
So in this case, it's a gas being excited. Okay? And it actually, you don't have to have any powder in there. The gas is excited and has a range of transitions from its excited state back down that give you those bands. Okay? So those are basically atomic transitions. Okay? Excited, coming back down. Inside these fluorescent bulbs, that's happening to generate a whole bunch of UV light. Okay? That's what's happening inside there, which then interacts with particles to give you the range of colors. But here it's a relatively pure color, and there's a certain set of discrete bands. So different gases in there would give you different colors. And the neon lights that you're used to seeing, those are that kind of a phenomenon. Okay, white LED, what'd you guys see? It wasn't discrete lines. You saw a band. Well, how about you guys?
We saw a band, but it was missing like the turquoise stuff.
So it was missing part of the spectrum, okay?
It was kind of like three distinct ones, but it was very bright in those parts, like the red, green, and blue, though they were, especially between like the red and green, like more connected.
Okay, so this LED, the way it's going to work, is it the type that is basically has a powder in it, or is it the type that's a red, a green, and a blue mixed together to give you white? You guys see how we came to that conclusion? Because it was an intense red, intense green, intense blue, and in between there was a little bit, but it wasn't as intense. So it wasn't like uniform, like looking at the sunlight, or looking at an incandescent light. It was more discrete. Okay, how about a colored LED? Who did a colored LED? Okay, what did you see? What color did you do, and what did you see?
Purple, and about 4 centimeters of leaves and stripes that went across to about 450, about like not as bright. And I don't know if this was something else exactly with this, but then we also got a stripe of like a rainbow that went from the purple one where it was most intense to red where it was thin and fresh.
I'd have to look. You might have had interference from something else, or there may be some leakage, maybe some variety of wavelengths.
And we got the same thing with purple. With
Okay.
the one band going out.
Okay, but a weak one. You got
There were,
a big
there were,
one.
like 5 like horizontal ones, like just in the like 410, like 430 like range, really bright, and like one of the 4 horizontal bands went all the way across.
We'll have to take a look. Okay. Anyone do a different color, like a red or a green or yes? So the thing to notice here is these bands are very broad, medium broad, very narrow. What are they? Medium broad. Kind of like they're not just a little line like you saw with the fluorescence, and they're not the whole spectrum. They're somewhere in the middle, right? That's the thing about LEDs. Okay. So how about the light stick? What does the light stick give you guys?
Kind of a range really dim between like 500 and 600.
Okay. So a range of wavelengths, but not again the whole spectrum. A range focused on the color you're getting. How about the black light? What did you guys see?
We had 2 like distinct vertical bands in the like low 400, and then it kind of like dimmed down past 400 to like 370.
So which black light did you use?
We used
Okay, see which black light they used? The one that has a bulb on it, long bulb. Okay. Did anyone else use the black light that's the little mini mag light type? What did you guys
It
get?
was more like a really strong line at like 400 and kind of fading off to 500 or so.
So yours is like a gas being excited. Yours is an LED. Okay? So yours gives a broader band. Yours will give some discrete bands. And believe it or not, it would also give some in the infrared, but you can't see those with your eyes. Okay, anyone do the phosphorescent patch? And what did you see there? I know some of you did it. I saw it. What did you see?
We just got like a really, really dim, like a green, like around 5.
Was it narrow, broad, just medium? What was it?
It was extremely.
Yeah, so it was hard to tell. Anyone else have any better luck seeing it?
we got kind of rainbow between 450 and really faint, so that's the kind of thing.
Okay. Okay. So it's relatively broad, what it gives you with the phosphorescence. And how about the lasers? What did you guys see? What did the lasers give you?
A very bright dot.
A very bright dot. Where were they? What color and where was it?
It was a red, it was bright at like 616, I guess 660, 650.
Anyone else get that? Okay, how about the green one? Who tried the green one? Okay, what'd you guys get?
It was just like one vertical band of like 550.
Great, perfect. So you notice the laser is very discrete, kind of like the same discreteness as what you get from some of those different chemical reactions or the flamingo, pink flamingo. Very discrete, but a single line. Okay? And if you look at the lasers, they tell you the wavelength they emit. Okay? So most of those will say something like 540, 550 nanometers, or they'll say 650, 654. Okay? That wavelength is very relevant. Yes?
What's the part of this little, it's right above the button? It's like a little clear.
Oh, just tell you whether it's on or not. I think it lights up.
Yeah.
Yeah, I'll tell you if it's working. Okay? So you guys got to see a range of different light sources, okay, and see what characteristics they have. And that's going to be very important because if you're studying some living tissue and you shine a green laser on it and the light coming off of it is red, what might you think is happening? And it's kind of broad. What would you think might be happening? You'd be getting some kind of fluorescence. But if you shine a incandescent light on some living tissue and you see what comes through, you know that a whole range of wavelengths are interacting with that tissue. If you were shining just the green laser, you know that it's a very narrow band of energies that's interacting with the tissue. Okay? So it's important to be aware of how these different light sources, what they put out. Okay? Okay, so with that said, we're out of time.